A world sits less than 100 million kilometers from Earth at its nearest, close enough to feel almost familiar, and yet it remains one of the least explored planets we know. From far away, Mercury looks simple, like a burned version of the Moon. A gray stone, a cratered relic, a place where the Sun has already won. But that picture is wrong in almost every interesting way. Mercury has ice hiding in permanent darkness, a magnetic field that should be too weak to matter, and a ghostly tail of atoms stretching millions of kilometers into space. The closest planet to the Sun is not just being baked, it is being stripped apart. I'm Christopher, and you're watching Sleepy Explorer. Stay with me, because Mercury is not the dead little world most of us were taught to imagine. It is a planet caught in a constant physical argument with the Sun, and the evidence is written across its surface, around its magnetic field, inside its craters, and even in the faint material it leaks into space. For a long time, Mercury had a strange problem. Everyone knew its name, but almost no one really knew the planet. It was the first planet from the Sun, the small inner world that appeared in school diagrams as a plain gray dot. It had no great rings, no thick clouds, no oceans, no moons, no obvious drama. It was easy to think of it as a leftover rock, scorched, silent, and finished. That assumption made sense from Earth. Mercury never moves far from the Sun in our sky, so it is often swallowed by glare. When it does appear, it shows itself near dawn or sunset, low on the horizon, difficult to observe clearly. Ancient people saw it. Astronomers tracked it. But for most of human history, Mercury remained more like a rumor with an orbit than a place. Even the spacecraft era did not change that quickly. Venus was visited early. Mars became a target again and again. Jupiter, Saturn, Uranus, Neptune, comets, asteroids, and moons all received attention while Mercury waited. This seems strange until you understand the trap. Mercury is close, but it is close to the wrong thing. It lives deep in the Sun's gravity. That one fact changes everything. To reach Mercury, a spacecraft does not simply aim inward and fall. Falling toward the Sun makes the spacecraft faster. By the time it reaches Mercury's neighborhood, it can be moving so quickly that the planet cannot catch it. Instead of entering orbit, the spacecraft would swing past and keep diving through the inner solar system, pulled along by the star that dominates everything nearby. So Mercury became a paradox for exploration. It was near enough to tempt us, but hard enough to delay us for decades. The first close look came from Mariner 10 in the 1970s, and even then it only saw part of the planet. The deeper transformation had to wait until Messenger, the first spacecraft ever to orbit Mercury, arrived in 2011. And when Messenger finally stayed, the plain gray dot began to fall apart. The first surprise was that Mercury did look familiar, but only at the surface. It was covered in craters, basins, ridges, and bright rays, like a smaller cousin of the Moon. But the resemblance was misleading. Mercury is far denser than the Moon. It carries a giant iron core, so large compared with the planet itself that Mercury is more metal-rich than any casual glance would suggest. That core matters because Mercury has something unexpected for such a small world. It has a magnetic field, not a strong one like Earth's, and not a protective shield that would make the surface safe, but a real field generated from within. It is weak, offset, and still not fully explained. Yet even in that fragile form, it changes the way Mercury interacts with the solar wind. The solar wind is a stream of charged particles flowing outward from the Sun. Near Earth, Our magnetic field stands far out into space and diverts much of that flow around us. Near Mercury, the Sun's pressure is much stronger, and Mercury's shield is much weaker. Its magnetosphere is compressed close to the planet, almost pressed down toward the surface. That makes Mercury's space environment restless. Magnetic field lines can break and reconnect. Charged particles can rush inward. Surface atoms can be knocked loose. The planet sits in a place where sunlight, particles, gravity, and rock are constantly trading energy. And that is where Mercury stops feeling dead. A dead planet should not seem to be leaking. Mercury does. Its exosphere, an atmosphere so thin that its atoms barely interact with one another, is constantly being lost and constantly being replaced. Some particles come from the surface when sunlight heats and loosens them. Some are knocked free by the solar wind. Some are released when tiny dust grains and micrometeoroids slam into the ground without any air to slow them down. There is no weather on Mercury in the way we understand weather. No wind pushing dust across plains, no rain smoothing stone, no clouds passing over the morningside. But there is still a kind of space weather, and it reaches all the way down to the surface. The sun does not just shine on Mercury, it scrapes it. That scraping becomes visible in one of Mercury's strangest features. The planet has a tail. Not a tail like a comet's bright flowing plume of ice and dust. Mercury is not an icy body boiling away as it nears the sun. Its tail is subtler, thinner, and stranger. It is made largely of sodium atoms, pushed away from the planet by sunlight itself. Under the right conditions, with the right filters, astronomers can see that sodium glow stretching far behind Mercury into space. Imagine that for a moment. A rocky planet, long known to humanity, close enough to appear in ancient skies, dragging an invisible stream behind it like a secret signature. The feature is enormous, yet hidden from ordinary sight. It was not discovered because it was obvious. It was discovered because instruments learned how to look for one specific kind of light. That is one of the themes of Mercury. The planet does not give up its truth easily. Its most important features tend to hide behind glare, darkness, faint signals, or misleading simplicity. Even its ice is like that. Mercury is the closest planet to the Sun, but some of its polar craters contain regions where sunlight never reaches the floor. Because the planet's axial tilt is almost non-existent, those deep pockets of shadow can remain cold for immense stretches of time. There, in a world famous for heat, water ice can survive. That single fact breaks the easy story. Mercury is not simply hot, it is extreme. On the day side, the surface can become hot enough to punish metal, electronics, and stone. On the night side, with no thick atmosphere to move heat around, the ground can plunge into deep cold. Near the poles, permanent darkness creates a different planet inside the planet, a set of hidden cold traps beside the solar furnace. Then there is the surface itself. Messenger showed that Mercury is not just cratered, it is scarred by shrinkage. As the interior cooled over time, the planet contracted, and its crust wrinkled into long cliffs and ridges called scarps. Some stretch for hundreds of kilometers. They are not decoration. They are evidence that the whole planet changed size. Other places show signs of ancient lava. Impact basins were flooded. Smooth plains spread across battered terrain. Bright patches may point to volcanic eruptions from billions of years ago. Strange hollows appear in many places. Shallow, irregular depressions that seem geologically young and may be connected to volatile materials escaping from the surface. That word matters. Volatile. Mercury should have been the last place to surprise scientists with substances that are easily lost under heat. And yet, Messenger found that Mercury's surface contained more of some volatile elements than older ideas about its formation expected. That forced scientists to rethink parts of the story. A planet so close to the Sun was not supposed to preserve such a chemical memory so well. So Mercury became something more difficult than a burnt rock. It became a test of how rocky planets form, how they lose material, how magnetic fields survive, how surfaces age, and how close a world can live to a star while still keeping secrets. This is why BepiColombo matters. The mission was built to return to Mercury with sharper tools and a deeper plan. Its orbiters are meant to study the planet's surface, interior, exosphere, and magnetic environment in ways Messenger could not fully do alone. Messenger gave us the first complete Mercury. BepiColombo is meant to ask why that Mercury exists at all. And that question is bigger than one small planet. Mercury is part of the same inner solar system as Earth. It formed from the same ancient disk of material around the young Sun. It was shaped by impacts, heat, gravity, chemistry, and time. If we misunderstand Mercury, then our picture of rocky planets is still incomplete. The strange thing is that Mercury has been in front of us the whole time. It was never hidden in the distant outer dark. It was not waiting beyond Neptune or buried in another star system, or visible only through the largest telescopes. It was right there, close to the Sun, seen since antiquity, named by ancient people, placed in every basic map of the planets. And still, the closer we get, the more it resists the simple version. It has ice where there should be heat. It has a tail where there should be a dead rock. It has a magnetic field where a small slope planet seems unlikely to keep one. It has a surface that looks ancient but still hints at active loss, contraction, and chemical change. Mercury is not dramatic because it is loud. It is dramatic because it is quiet while the Sun works on it. Every particle knocked loose, every shadowed crater, every magnetic twitch, every bright ray across the surface is part of the same story. A small planet is surviving in a place where survival leaves marks. To understand those marks, we first have to understand why getting to Mercury is so difficult in the first place. Because the real wall around the closest planet was never distance. It was speed. Speed is what makes Mercury deceptive. On a map of the solar system, it looks like the easy target. Earth is here, the Sun is there, and Mercury is the small inner planet moving between them. It feels as if a spacecraft should simply fall inward, cross the empty distance, and arrive. But spacecraft do not move across the solar system the way arrows move across a drawing. They move through gravity, and near Mercury, gravity has one overwhelming owner: the Sun. The closer a spacecraft falls toward the Sun, the faster it moves. That is not a flaw in the mission design. It is the natural result of falling into the deepest gravitational well in the solar system. A probe heading inward gains energy the same way a stone gains speed as it falls down a cliff. By the time it reaches Mercury's orbit, it may be moving far too fast for Mercury to capture. This is the part that makes Mercury so difficult. The challenge is not reaching the neighborhood. The challenge is arriving there without tearing through it like a bullet. If a spacecraft comes in too fast, Mercury cannot hold it. The planet's gravity is too small compared with the Sun's pull. Instead of settling into orbit, the spacecraft swings past, bends around the planet, and continues on a new path around the Sun. To truly study Mercury, a mission has to do something much harder than travel inward. It has to bleed away speed. And bleeding away speed in space is expensive. Every kilogram of propellant carried by a spacecraft has to be launched from Earth. Every kilogram of propellant also means less mass available for cameras, spectrometers, magnetometers, thermal shields, antennas, wiring, and the instruments that actually make the journey worth taking. So the old problem was brutally simple. To enter orbit around Mercury, a spacecraft seemed to need too much fuel, but if it carried enough fuel, it would become too heavy to launch efficiently or too compromised to do the science. For decades, that was the wall. Mariner 10 reached Mercury in the 1970s, but it did not enter orbit. It flew past, and even that was a major achievement. It gave humanity its first close views of the planet, revealing a cratered, battered surface that resembled the moon at first glance. But Mariner 10 saw only a part of the world. Much of Mercury remained unmapped, unmeasured, and unknown. Then came the idea that changed the problem. Instead of fighting the sun with raw fuel, a spacecraft could use the planets themselves as part of the braking system. This is one of the quieter forms of elegance in spaceflight. A gravity assist is often described as a slingshot because spacecraft can use a planet's motion to gain speed. But the same kind of encounter can also be used in reverse. A spacecraft can pass near a planet in a carefully shaped path and give up some of its orbital energy. It is not touching an atmosphere. It is not applying brakes like a car. It is exchanging motion with a world. The planet barely notices, or the spacecraft notices everything. That was the path Messenger took. Launched in 2004, Messenger did not fly straight to Mercury and stop. It looped through the inner solar system, returning once to Earth, passing Venus twice, and flying by Mercury several times before finally slowing enough to enter orbit in 2011. The journey took years not because engineers got lost, but because they were using time, gravity, and geometry as fuel. There is something almost patient about that. To reach the closest planet properly, Messenger had to avoid the obvious route. It had to fall inward carefully, circle the sun again and again, meet planets at the right moments, and let each encounter shave away just enough speed. The mission was small compared with many famous deep space probes. It had to be. It carried a heat shield to protect itself from the sun, solar panels that could be angled and used with care, and a set of scientific instruments designed to learn as much as possible from a world no spacecraft had ever orbited before. Its full name was Mercury Surface, Space Environment, Geochemistry, and Ranging, but the short name was fitting. Messenger was being sent to a planet that had waited a long time to speak clearly. Even before it arrived, the spacecraft had to survive the conditions that made Mercury difficult in the first place. Near Mercury, sunlight is not just light, it is a force. It heats spacecraft surfaces, drives thermal expansion, pushes very slightly on solar panels, and demands constant attention from mission designers. Messenger used the pressure of sunlight in subtle ways, letting its solar panels act almost like controlled sails. The push was tiny, but over a long journey, tiny pushes can become real navigation. That is one of the strange lessons of space. A force too small to feel in a human hand can matter across millions of kilometers. Messenger's path also carried moments of uncertainty. During one Mercury flyby before orbital insertion, the spacecraft entered safe mode. Safe mode is a protective state, the machine pulling itself inward, preserving essential systems when something has gone wrong or become unclear. For people on Earth, it is the kind of phrase that sounds calm only because it has to. Behind it is a spacecraft far from home, near the sun, at the edge of a mission years in the making. Messenger recovered. It continued. And in March of 2011, It became the first spacecraft ever to orbit Mercury. That sentence sounds simple. It was not. To orbit Mercury, Messenger had to live between two sources of heat. One was obvious: the Sun, blazing far stronger there than it does near Earth. The other was Mercury itself. The planet's surface absorbs sunlight and radiates heat back into space, so a spacecraft passing close above it can be warmed from below as well as from the side facing the Sun. Messenger's orbit was shaped partly around survival. It would come close to the surface, then swing far out again, giving itself time to cool. The spacecraft was not just looking at Mercury, it was enduring Mercury. For 4 years, it mapped, measured, and listened with instruments. It returned more than 200,000 images. It turned a partial planet into a global one. It showed the northern plains, the giant basins, the long scarps, the hollows, the strange colors, the chemical surprises, and the evidence that Mercury had once been much more geologically active than its quiet appearance suggested. But Messenger also revealed the limits of a single mission. Its orbit gave better coverage to some regions than others. Its instruments transformed Mercury's science, but every answer opened a sharper question. Why was the magnetic field offset? Why were volatile elements so abundant on a planet so close to the Sun? How were hollows forming? What exactly was happening in the exosphere? How did the surface, interior, magnetic field, and solar wind all fit together? That is why BepiColombo was built. BepiColombo is not one simple spacecraft in the ordinary sense. It is a combined mission from the European Space Agency and the Japan Aerospace Exploration Agency, traveling as a stacked system before separating into orbiters around Mercury. One orbiter is designed to study the planet's surface and interior. The other, called MEO, is built to study Mercury's magnetic environment and the flow of charged particles around it. That matters because Mercury cannot be understood from one viewpoint alone. The planet is small, but the system around it is fast, compressed, and restless. Solar wind conditions can change. Magnetic boundaries can shift. Particles can surge. If one spacecraft sees a change, it may be hard to know whether that change happened because the spacecraft moved through space or because the environment itself changed over time. Two orbiters can begin to separate those possibilities. But before BepiColombo can do that, it has to solve the same old Mercury problem. It has to slow down. So, its journey, like Messenger's, is long and indirect. After launching from Earth, it follows a carefully planned route through the inner solar system, using planetary flybys and solar electric propulsion to reduce its speed relative to Mercury. It passes Earth, Venus, and Mercury itself, not as detours from the mission, but as the mission's braking system. Each flyby is a small correction in a long argument with the Sun. From a human point of view, this can feel backwards. We tend to measure difficulty by distance. The farther something is, the harder it seems. But Mercury teaches a different rule. In spaceflight, closeness can be dangerous. Going inward is not like walking downhill. It is like descending into a current that keeps pulling faster. The Sun is the current. A spacecraft heading to Mercury has to do more than survive heat. It has to arrive with the right energy, at the right angle, at the right moment, after years of carefully arranged motion. One wrong assumption about speed can turn an orbiter into a flyby. One missed chance to slow down can leave the planet behind. This is why Mercury remained underexplored for so long. Not because it was boring, not because scientists lacked questions, but because the closest planet sits behind one of the most difficult gates in planetary exploration. And once Messenger finally crossed that gate, it found a world that was not waiting passively under the sun. It found a planet built around a giant core. That core is where Mercury begins to stop looking like a smaller moon. The moon is rocky through and through, with a small metallic heart compared with its overall size. Mercury is different. Beneath its battered crust sits an enormous iron-rich interior, so large that it takes up most of the planet's radius. If you could peel Mercury open, the first surprise would not be how scorched it is. The first surprise would be how much of it is metal. That one fact changes the entire story. Mercury is small enough that, at first glance, it should have cooled quickly. Small bodies lose internal heat more easily than large ones. Their interiors freeze. Their engines shut down. Their surfaces become records of things that happened long ago, not signs of forces still shaping the present. And in many ways, Mercury does look like that kind of body. Its face is ancient, cratered, and still. But Messenger found that Mercury had kept more internal life than expected. The spacecraft carried instruments that could map gravity, measure the magnetic field, read the chemistry of the surface, and photograph the terrain in detail. Piece by piece, those instruments began to describe a planet whose outer silence was hiding a complicated interior. Mercury was not just a rocky shell sitting beside the sun. It was a dense, metal-heavy world with a core that still mattered. The magnetic field was the first clue. Earth has a magnetic field because deep inside our planet, moving liquid metal helps generate a dynamo. That field reaches far into space and forms a protective magnetic bubble around us. Mercury's field is much weaker, but its existence points to something similar happening inside the planet. Somewhere beneath the crust and mantle, part of Mercury's metallic core appears to remain fluid enough to help generate magnetism. That is strange because Mercury rotates slowly. It has no large moon needing it the way our moon raises tides on Earth. It is small, old, and exposed. Yet the field is there. Weak, but real. Messenger did not simply confirm that Mercury had magnetism. It showed that the field was offset from the planet's center. That is not a small detail. A magnetic field is like a fingerprint of the engine producing it, and Mercury's fingerprint does not line up neatly with the middle of the planet. The field is shifted northward, leaving the southern hemisphere more exposed to the solar wind than the northern side. That asymmetry matters because Mercury already lives under extreme pressure from the sun. The solar wind near Mercury is stronger than it is near Earth, and the planet's magnetic shield is much smaller. Instead of expanding far into space, Mercury's magnetosphere is compressed close to the surface. It is like a thin umbrella held against a storm. Most of the time, it deflects some of the charged particles flowing outward from the sun. But the protection is incomplete. The solar wind can push, twist, and reconnect magnetic field lines, opening pathways that allow particles to rush down toward the planet. Messenger saw a space environment that was not calm, but twitching, pulsing, and constantly being rearranged. That was one of the mission's deeper achievements. It did not just show Mercury as a surface, it showed Mercury as a system. A planet is not only the rock you see in photographs. It is the interior that creates the magnetic field. It is the magnetic field that shapes incoming particles. It is the surface that releases atoms when those particles strike. It is the thin exosphere that forms and disappears because nothing is dense enough to hold it together. At Mercury, all of those layers are pressed close together by the sun. Messenger let scientists watch those layers interact. Its instruments found bursts of energetic particles. They traced changes in the magnetic environment. They measured elements in the exosphere and surface. They showed that Mercury's surface was rich in substances that should have been difficult to preserve so near the Sun. Potassium, sulfur, sodium, chlorine, and other volatile materials appeared in amounts that challenged older expectations. That was not just a chemistry footnote. It was a formation problem. For a long time, it was tempting to imagine Mercury as a planet stripped down by heat. So close to the Sun, you might expect the light, easily lost materials to be gone, cooked away during formation or blasted off over billions of years. But Messenger showed a more complicated picture. Mercury had clearly lost material, but it had also kept chemical fingerprints that did not fit the simplest version of a scorched leftover world. The planet was not just missing things. It was preserving things it was not supposed to preserve. That forced scientists to look again at how Mercury formed. Maybe it formed from materials that were already unusual. Maybe a giant impact removed part of its outer layers. Maybe the early solar environment sorted material in a way older models did not capture. None of those explanations is simple, and none can be treated as the whole answer without caution. The important point is that Messenger turned Mercury into a question about beginnings, and its surface added more questions. Before Messenger, large parts of Mercury had never been seen in high detail. Mariner 10 had revealed enough to show that Mercury was cratered and ancient, but not enough to build a complete geological story. Messenger changed that. It mapped the full planet. It photographed impact basins, smooth plains, volcanic features, long cliffs, bright rays, dark deposits, and strange shallow pits called hollows. The hollows were especially unsettling in a quiet way. They are irregular depressions, often bright-rimmed, often appearing fresh compared with older terrain around them. They do not look like ordinary impact craters. They do not fit neatly into the idea of a surface that has been unchanged for billions of years. One leading idea is that they form when volatile materials escape from the rocks, leaving the surface to collapse or erode in place. If that is right, Mercury's surface is still losing pieces of itself. Not dramatically, not with rivers or winds or storms, but through chemistry, heat, radiation, and exposure. A hollow is not a volcano. It is not a crater. It is a small mark left by a planet being altered in the open. Messenger also found evidence of enormous volcanic plains. Some regions had been flooded by lava long ago, smoothing the floors of basins and filling lowlands across huge areas. That was another break from the simple moon-like image. Mercury was not merely bombarded. It had once melted, erupted, flowed, cooled, and hardened into new terrain. The planet had also shrunk. Across Mercury's surface are long, cliff-like ridges called lobate scarps. They formed as the planet's interior cooled and contracted, causing the crust to wrinkle and break. Imagine the skin of a fruit tightening as the inside dries and shrinks. The comparison is imperfect, but it gives the feeling. Mercury's outer shell had to adjust as the inside lost heat. Messenger showed that this contraction was larger than earlier estimates suggested. Mercury had not just cooled a little, it had tightened around itself. That image is hard to forget. A world beside the sun, cooling from within, shrinking under its own history, while its surface is struck from above and stripped from outside. Messenger's orbit made this portrait possible, but the orbit itself was a compromise. The spacecraft followed a long, stretched path around Mercury. It would pass close over the planet, then swing far away again. This allowed it to gather high-resolution data while avoiding too much heat. Mercury and the Sun together created a harsh thermal environment, and the spacecraft had to survive as carefully as it observed. For 4 years, Messenger did that work. It returned more images than anyone had expected. It mapped the globe. It measured the magnetic field. It found evidence for water ice in permanently shadowed polar craters, confirming that even the closest planet to the Sun could preserve frozen material in the right kind of darkness. It studied the exosphere and showed how atoms from the surface could be lifted, scattered, and carried away. Then, after years of careful maneuvering, its propellant finally ran out. Messenger had always been temporary. Every orbit required management. Every correction drew from a limited supply. Near the end, the spacecraft was brought lower and lower, gathering final close measurements as long as it could. In April of 2015, it struck the surface of Mercury, ending its mission by becoming part of the planet it had revealed. There is something fitting about that. Messenger arrived because engineers found a way to slow a machine against the Sun. It survived years above a world that was never gentle to it. Then it left behind not just a crater, but a changed understanding. Before Messenger, Mercury was the first planet in order. After Messenger, it became one of the strangest rocky worlds we know. But the mission also left gaps. Its orbit favored some regions more than others. Its measurements opened questions that required more than one spacecraft, better coverage, and simultaneous views of Mercury's surface and magnetic environment. It gave scientists the first complete Mercury, but completeness is not the same as explanation. The planet's giant core, weak magnetic field, volatile surface, polar ice, sodium tail, hollows, scarps, and ancient lava plains were no longer isolated curiosities. They were pieces of one unfinished puzzle. To solve that puzzle, we have to look more closely at the planet itself. Not just where it is, what it is made of. What it is made of is the first clue that Mercury is not a small moon beside the Sun. The Moon is light compared with Mercury. Ganymede and Titan are both larger than Mercury across, yet Mercury contains far more mass than either of them. Its size says one thing. Its weight says another. That mismatch is where the planet becomes interesting. Because Mercury is not simply a rocky ball with a small metal center, it is a metal-rich world wrapped in a comparatively thin outer shell. Most rocky planets have iron cores. Earth does. Venus does. Mars does. But Mercury's core is unusually large for the size of the planet, so large that it dominates the interior. If Mercury were scaled up to Earth's size without changing its density, its surface gravity would be far closer to Earth's than its small appearance suggests. As it is, Mercury's gravity is still weaker than Earth's, but only a little weaker than Mars, even though Mars is much larger. That tells you something important. Mercury is compact, dense, heavy for its size. The obvious question is why? One possibility is that Mercury formed from material that was already unusually rich in metal. Another is that early in its history, some violent event stripped away part of its outer rocky layers, leaving a planet with a core that seems oversized. Another is that the young sun's heat and the early solar nebula sorted materials in ways that made Mercury different from the start. Scientists still debate the details, and Messenger did not close the case. It made the mystery sharper. Because Mercury is not just dense, it is chemically surprising. If it had been stripped down by extreme heat alone, scientists might expect many easily lost elements to be greatly depleted. Yet Mercury kept unexpected amounts of volatile substances, including sulfur, potassium, sodium, and chlorine. Those are not details you can casually ignore. They are fingerprints of formation, and they do not match the simplest story of a planet baked clean by the sun. So Mercury forces two ideas to sit together uneasily. It is metal-rich, as if something removed or reduced its rocky outer layers. But it is also volatile-rich in ways that suggest it was not simply scorched empty. That is the kind of contradiction that makes a planet useful. It does not let the old model rest. The surface tells a related story. At first, the cratered landscape looks inactive, almost fossilized. But when scientists began mapping it in detail, they found signs that Mercury's outer shell had been shaped by forces both above and below. Impacts came from space. Lava came from inside. Contraction came from cooling. And sunlight kept working on the chemistry of exposed rock. The result is a planet that looks motionless only because its motion happens on a scale too slow for human senses. A day on Mercury is one of the strangest examples of that slow, hidden motion. The planet takes about 88 Earth days to orbit the Sun, but it rotates once in about 59 Earth days. Those two movements are locked in a 3-to-2 rhythm. Mercury turns 3 times for every 2 orbits around the Sun. That sounds like a technical detail, but on the surface it would become a deeply strange experience. If you could stand safely on Mercury, the Sun would not behave the way it does on Earth. It would rise, move across the sky, slow down, and near certain points in Mercury's orbit, appear to pause. Then, because Mercury is moving fastest when it is closest to the Sun, the apparent motion of the Sun could briefly reverse before continuing again. The sky would seem to hesitate. This happens because Mercury's orbit is not a neat circle. It is the most stretched orbit of any major planet in the solar system. At its closest point to the Sun, Mercury moves much faster than it does at its farthest point. The planet's rotation continues steadily, but its orbital speed changes enough to distort the Sun's path across the sky. That one fact turns the surface into something alien in a way photographs cannot fully show. On Earth, sunrise and sunset are familiar rhythms. On Mercury, a solar day lasts roughly 2 Mercury years. A single stretch from sunrise to sunrise would take 176 Earth days. Half of that is daylight, half is night. This is why Mercury cannot be described as only hot. It is more precise to say it is thermally divided. On the day side, the ground can become hotter than 400 degrees Celsius. On the night side, with no thick atmosphere to carry warmth around the planet, the temperature can collapse far below freezing. Mercury receives fierce sunlight, but it cannot store or spread that heat the way an atmosphere can. The planet is exposed in both directions. In daylight, the surface bakes. In darkness, it radiates heat away into space. The same planet can be furnace and freezer, depending on where and when you stand, and near the poles. The situation becomes even stranger. Mercury's axis is almost upright. It has almost no tilt. That means some deep crater floors near the poles never receive direct sunlight at all. Their rims may be exposed to the glare, but their interiors remain in permanent shadow. Inside those shadowed pockets, temperatures can stay cold enough for water ice to survive. There is something quietly wrong about that image, which is why it matters. Ice on the closest planet to the Sun sounds like a mistake until you understand the geometry. The Sun is not absent from Mercury. It is overwhelming. But light travels in straight lines, and a crater wall can become a shield. In a place with almost no air, heat cannot easily drift into those shadows. Darkness becomes insulation. Radar observations from Earth hinted at bright reflective deposits near Mercury's poles before Messenger confirmed that the reflections matched permanently shadowed regions. The leading interpretation is water ice, likely mixed in places with darker material. Where that water came from is still debated. Comets and asteroids may have delivered some of it. Some may have been produced or redistributed by surface chemistry and solar wind interactions. The important part is that Mercury can keep it. The smallest details of shape create the largest contrast. A crater rim a few kilometers high can separate sunlight intense enough to bake rock from darkness cold enough to preserve ice. That is Mercury in miniature. It is never just one environment. It is a world of extreme boundaries. The same is true of its atmosphere, though atmosphere is almost the wrong word. Mercury has an exosphere, a veil so thin that the particles in it rarely collide with one another. On Earth, air behaves like a fluid. It swirls, presses, mixes, and carries sound. On Mercury, there are atoms above the surface, but not enough for weather, breath, clouds, or wind. Each particle is almost alone. And because that exosphere is so thin, it is temporary. It has to be constantly replenished. Solar wind particles strike the surface and knock atoms loose. Sunlight helps lift material. Tiny impacts vaporize rock. Some particles fall back. Some escape. Some are pushed into Mercury's tail. The surface and the space around it are connected almost directly. On Earth, the atmosphere is a buffer. On Mercury, the buffer is nearly gone. The sun reaches the ground with little interruption. Charged particles, ultraviolet light, micrometeoroids, and radiation all interact with the exposed surface. The boundary between planet and space is not clean. It is an active exchange. This gives Mercury a strange kind of vulnerability. Not the vulnerability of life, because there is no known life there. Not the vulnerability of oceans or weather or fragile biology. It is the vulnerability of bare matter under constant attack. Rock can seem permanent from a human point of view, but give sunlight, particle radiation, impacts, and time enough room to work, and even rock becomes a slow source of atoms. That is why Mercury's chemistry matters so much. Sodium on the surface can become sodium in the exosphere. Calcium can appear in patterns that change with local time. Hydrogen and helium can arrive from the solar wind. Magnesium and other atoms can be observed escaping from different regions. The planet is not sealed. It is porous to space in a physical sense. Every part of Mercury's identity feeds another part. Its high density points to its interior. Its interior creates a magnetic field. That magnetic field shapes the solar wind. The solar wind strikes the surface. The surface releases atoms. Those atoms form the exosphere and the tail. The same sunlight that heats the day side also pushes loose material away. The same near-zero tilt that creates permanent polar shadows allows ice to survive beside a star-facing furnace. Mercury is not a collection of odd facts. It is a connected machine. But the machine is old, damaged, and incomplete to us. We can see its pieces, but we do not yet fully know how they all fit. Its giant core asks how the planet formed. Its volatile-rich surface asks what it kept and why. Its ice asks how material is delivered and preserved. Its day asks how orbital motion can rewrite the meaning of sunrise. Its exosphere asks how a nearly airless planet can still lose material in a visible way. And all of those questions lead to the same faint glow trailing behind it. Because Mercury's most delicate feature may be the one that reveals the sun's grip most clearly. Its ghost tail is almost invisible until you know exactly what kind of light to look for. Through an ordinary telescope, Mercury does not look like a planet with a tail. It looks like a small bright disk near the sun, often difficult to separate from glare, often too low in the sky to study comfortably. Nothing about it announces that atoms are streaming away behind it. Nothing about the visible planet suggests a structure so long that it can reach millions of kilometers into space. That is what makes the discovery so strange. Mercury had been seen since ancient times. It had been visited by spacecraft. It had been measured, named, mapped in pieces, placed in diagrams, and treated as one of the familiar inner planets. Yet one of its largest features remained hidden until astronomers learned to isolate a very specific glow. The glow came from sodium. Sodium is not rare in daily life. It is part of ordinary salt. It is also responsible for the yellow-orange color of old streetlights, the kind that once made city roads look warm and slightly unreal at night. In Mercury's case, sodium atoms above the surface can absorb sunlight and then release light at a very specific wavelength. To human eyes, the signal is too faint and too buried under other light to stand out. But with special filters that block nearly everything except sodium's glow, the hidden structure appears. And then Mercury stops looking like a dead stone. The tail stretches away from the sun, trailing behind the planet through space. It is not thick. It is not something you could fly through like smoke. It is made of scattered atoms in a near vacuum, so thin that ordinary language almost makes it sound denser than it is. But it is real, measurable, and enormous. Observations have shown it extending about 2.5 million kilometers from Mercury. For a planet less than 5,000 kilometers wide, that is not a small feature. The easy comparison is a comet, but the comparison can mislead. A comet's tail usually begins with ice. As a comet approaches the sun, frozen material warms and turns directly into gas, dragging dust and charged particles outward. The result can be a long, bright plume shaped by sunlight and the solar wind. Mercury is different. It is a rocky planet. It is not an icy snowball entering the inner solar system for a brief dramatic passage. It lives there permanently. Its tail is not created by the boiling away of a large frozen body. It is created by the slow removal of atoms from exposed rock. That makes the tail quieter, but in a way, more unsettling. Because it means the sun is not just lighting Mercury. It is helping take Mercury apart, atom by atom. One of the main processes is sputtering. The word sounds technical, but the idea is simple. The solar wind carries charged particles outward from the sun at enormous speed. Near Mercury, those particles arrive with much less distance behind them than they have by the time they reach Earth. They strike a planet with almost no atmosphere to soften the impact. When they hit Mercury's surface, they can transfer energy into the uppermost material. If enough energy reaches a weakly held atom, that atom can be knocked free. It is a little like striking a dusty surface with a spray of invisible microscopic projectiles. Most of the surface remains, but some atoms are shaken loose and lifted into the exosphere. Sodium is one of the elements that can be released this way. The process does not need wind in the ordinary sense. It does not need air. It does not need clouds, pressure, storms, or sound. It only needs an exposed surface, incoming particles, and time. Mercury has all three. Micrometeoroids add another source. These are tiny pieces of space debris, many no larger than dust grains, moving fast enough to matter. On Earth, small particles often burn in the atmosphere before reaching the ground. On Mercury, there is no protective air thick enough to stop them. They strike the surface directly. Each tiny impact can vaporize a little bit of material. A dust grain becomes an event. A speck becomes a hammer. The surface flashes at a scale no human standing there could survive, and atoms are released into the exosphere. This is Mercury's version of erosion. Not rivers cutting valleys, not rain wearing down stone, not wind moving sand over dunes. This is space erosion, driven by sunlight, charged particles, and impacts too small to see from far away. The planet's surface is being weathered by the environment of the inner solar system itself. But releasing sodium is only the first step. Once sodium atoms are lifted from the surface, something has to shape them into a tail. That something is sunlight. Light does not feel heavy because photons have no rest mass, but photons carry momentum. When a sodium atom absorbs a photon from the sun, it receives a tiny push. Then it re-emits light, usually in a random direction, and is ready to absorb again. The random part tends to cancel out. The push from sunlight keeps coming from one direction, away from the sun. A single push is almost nothing. But again, Mercury teaches the power of small forces given enough time and exposure. Countless sodium atoms absorb light, receive tiny outward nudges, and gradually accelerate away from the planet. Mercury's gravity is weak enough that many of those atoms do not return. They are drawn out into a long anti-solar stream. It is not the solar wind blowing a gas cloud backward in the simplest sense. Radiation pressure from sunlight itself is one of the dominant sculptors. The same light that makes Mercury so difficult to observe also shapes the tail that Mercury hides. There is a quiet elegance in that. The sun creates the glare that conceals the planet, strikes the surface to help release atoms, and then pushes those atoms into the shape that finally reveals the interaction. The tail points away from the sun because the physics is directional. The planet moves around its orbit, the sun shines outward, and sodium responds. But the tail does not look equally bright all the time. It changes as Mercury moves. Mercury's orbit is stretched. At one point, it comes closest to the sun. At another, it moves farther away. Its speed changes along the way, faster near closest approach and slower when farther out. You might expect the sodium tail to look brightest when Mercury is closest to the sun, because sunlight and solar wind are strongest there. But the peak can come later. That detail is where the story becomes more delicate. The brightness of the tail is not controlled only by how much sodium is released. It is also controlled by how efficiently those sodium atoms can absorb and scatter sunlight in a way we can observe. Mercury's changing speed shifts the light in a subtle way, through the Doppler effect. When something moves relative to a source of light, the wavelength of that light can appear stretched or compressed. We often hear about this with distant galaxies or passing sirens, but the same basic idea applies here. As Mercury moves away from the sun after closest approach, the sunlight that reaches sodium atoms is shifted in a way that can make the atoms better able to scatter the specific light astronomers are looking for. So the tail can become more visible not simply when Mercury is being hit hardest, but when its motion creates the right optical conditions. That is a very Mercury kind of answer. The obvious explanation is close. The real explanation needs one more layer. There are also viewing conditions from Earth. Mercury has to be far enough from the sun in our sky that telescopes are not overwhelmed by glare. The geometry has to let us see the tail extending in a favorable direction. The planet cannot be hidden behind the sun from our point of view. The timing has to work across Mercury's orbit, Earth's orbit, and the direction of the sodium stream. In other words, the tail is not merely faint, it is selective. It appears clearly only when physics and perspective cooperate. That helps explain how such a large feature could go unnoticed for so long. Mercury's tail was not hiding because it was distant. It was hiding because we were not looking at the right wavelength, from the right angle, at the right time, with the right expectation. And expectation matters. If you think of Mercury as a dead cratered rock, you do not immediately imagine it leaving a chemical trace through space. If you think of tails as belonging mainly to comets, you do not expect one around the smallest planet. Discovery often begins when an instrument sees something that the old mental picture had no place for. The sodium tail gave Mercury a new identity. It showed that the planet's surface and space environment were not separate. They were connected in a constant exchange. The sun strikes the surface. The surface releases atoms. Light pushes those atoms outward. Telescopes on or near Earth catch the faint glow. A planet's erosion becomes a visible signal. This also makes Mercury useful far beyond itself. Airless bodies throughout the solar system can lose material in similar ways. The Moon has a faint sodium tail of its own. Other rocky bodies exposed to radiation and impacts may also release atoms into space. Around other stars, close-in planets may be stripped far more dramatically, leaving chemical signatures that telescopes can detect across interstellar distances. Mercury is nearby enough to study in detail, but extreme enough to teach a broader lesson. A star does not have to destroy a planet all at once. It can alter it slowly. It can shape its surface chemistry, thin its outer layers, drive escape, and leave behind clues in the light. That is why the sodium tail is not just a strange feature. It is a diagnostic. It tells scientists how Mercury interacts with the Sun today, and it hints at how that interaction may have changed the surface over billions of years. The present tail is faint, but the process behind it has been working for an immense span of time. Still, the tail is only one part of Mercury's exposed life beside the Sun. Some atoms leave, some return, some are ionized and swept into magnetic structures, some respond to radiation pressure, some trace the shape of the exosphere. The whole region around Mercury becomes a thin, restless borderland where surface, light, plasma, and gravity overlap. To understand that borderland, scientists need more than images. They need simultaneous measurements of particles, magnetic fields, ultraviolet light, surface composition, and solar wind conditions. They need to know what changes because Mercury rotates, what changes because it moves around the Sun, and what changes because the Sun itself becomes more or less active. That is where the next mystery waits. Because Mercury is not completely unprotected. It has a magnetic field, a weak one, an offset one, a strange one, but still a real shield generated from inside the planet. And near the Sun, even a weak shield can become a complicated thing. A weak shield sounds almost like no shield at all. Around Earth, the magnetic field reaches far outward, forming a broad protective region that stands between our atmosphere and much of the solar wind. It is not perfect protection, but it is large enough that Earth feels wrapped in something. Mercury does not have that luxury. Its magnetic field is much smaller, much weaker, and pressed close to the planet by the Sun. But weak does not mean simple. Mercury is the only rocky planet besides Earth with a global magnetic field generated from inside the planet. Venus does not have one in the same way. Mars once had a stronger global field, but today only pieces of ancient magnetism remain locked in parts of its crust. Mercury, small and slow as it is, still carries an active internal magnetic engine. That is the first mystery. A planet barely larger than our Moon, so close to the Sun, with a rotation so slow that one spin takes nearly 2 Earth months, should not feel like an obvious place for a living dynamo. Dynamos need moving electrically conductive material. In rocky planets, that usually means liquid metal deep inside. If the core freezes, the engine weakens or stops. Mercury's field tells us that something inside it is still moving. Not violently, not like a star, but enough. Somewhere below the crust and mantle, part of Mercury's metal-rich interior appears to remain liquid, or at least able to support the motion needed to generate magnetism. That alone makes Mercury a direct clue to planetary survival. It means the first planet from the Sun did not simply cool into a dead lump of metal and stone. The stranger part is the shape of the field. Messenger found that Mercury's magnetic field is shifted northward from the planet's center. If you imagine a bar magnet buried inside a world, you might expect it to sit more or less through the middle. Mercury's does not behave that neatly. Its magnetic equator is displaced, which means the field protects the planet unevenly. The northern and southern hemispheres do not meet the solar wind under the same conditions. That asymmetry has consequences. On the northern side, the magnetic field offers relatively more shielding. On the southern side, the surface can be more exposed. This matters because Mercury's environment is already compressed to an extreme. The solar wind does not meet a broad magnetic bubble the way it does at Earth. It hits a small, tight structure, one that can be pushed close to the planet's surface. The image is not of a strong wall. It is more like a thin, flexible membrane held against a storm. The storm is constant, but never exactly the same. The Sun sends out charged particles, magnetic fields, bursts, streams, and disturbances. Near Mercury, those changes arrive in a region where everything is crowded. The bow shock, magnetopause, magnetotail, and particle environment are all packed close to the planet. Boundaries that would sit far from Earth are squeezed inward. So when the solar wind changes, Mercury responds quickly. Magnetic reconnection is one of the key processes. The phrase can sound abstract, but the basic idea is physical. Magnetic field lines carried by the solar wind can meet Mercury's magnetic field in ways that let them break and reconnect into new shapes. When that happens, energy is released, and charged particles can gain access to regions they were previously blocked from. At Earth, magnetic reconnection helps drive auroras and geomagnetic storms. At Mercury, the same kind of process happens in a smaller, harsher system. The solar wind pressure is stronger, the magnetosphere is tighter, and the surface sits closer to the action. There is no thick atmosphere waiting below to absorb the consequences gently. Particles can be guided downward. They can strike the surface, they can knock atoms loose, they can help feed the exosphere. This is why Mercury's magnetic field cannot be treated separately from its tail, its surface chemistry, or its geological story. The field is weak, but it organizes the violence. It decides where particles enter, how energy moves, and which parts of the surface are more exposed at different times. Messenger gave scientists the first detailed look at this environment, but it also showed why one spacecraft could not answer everything. If Messenger measured a sudden change in magnetic conditions, scientists had to ask whether the spacecraft had flown into a different region or whether the region itself had changed while the spacecraft was there. In a small, dynamic magnetosphere, that distinction matters. This is where BepiColombo's design becomes important. The mission carries two orbiters that will eventually separate and study Mercury from different paths. One is focused on the planet itself, its surface, composition, interior, and gravity. The other, MEO, is focused on the magnetic and particle environment around Mercury. Together, they can help scientists compare what is happening near the surface with what is happening farther out in the magnetosphere. That difference is not just technical. It is the difference between seeing a single frame and watching a system breathe. If two spacecraft measure related changes from different locations, scientists can begin to separate space from time. They can ask whether a particle burst is local or global. They can see how magnetic boundaries move. They can watch how solar wind disturbances travel through Mercury's compressed environment. They can connect the invisible field above the planet to the atoms escaping below. And that connection is the heart of Mercury. On Earth, we are used to thinking of the surface, atmosphere, and magnetic field as layers with distance between them. The ground is down here. The weather is above it. The magnetosphere is far beyond. At Mercury, those layers are almost pressed together. The surface is exposed. The exosphere is fragile. The magnetic field is small. The solar wind is near. A change in space can become a change on the ground. That is not an exaggeration. Charged particles can impact Mercury's surface directly. They can alter grains of rock. They can release atoms. They can help create the temporary exosphere that is then shaped by sunlight. Some particles are ionized and swept away. Some neutral atoms are pushed into the sodium tail. Some fall back and strike the surface again. Mercury is recycling its own skin through space. This process is slow from a human point of view, but planets do not measure time the way we do. Over millions and billions of years, small losses matter. A faint exosphere can become evidence of long-term surface alteration. A weak field can influence where the alteration happens. A tail that appears almost ghostly through a telescope can become a record of a planet-star relationship. That is why the magnetic field is not merely a curiosity. It is a probe into the deep interior and the exposed surface at the same time. If Mercury's core is still partly fluid, why has it stayed that way? Its large iron core may have cooled differently from smaller bodies. Its composition may lower the freezing point of internal materials. Its eccentric orbit may produce subtle tidal flexing as the sun's pull changes over the course of Mercury's year. The details remain under study, and no single explanation should be made too neat. But the existence of the field tells us the planet's interior has not become fully silent. At the same time, the field's weakness tells us Mercury is not protected in the way Earth is. It lives in a halfway state, strong enough to shape the solar wind, too weak to keep the surface isolated from it, active enough to be scientifically rich, fragile enough to let the sun reach down. That halfway state may be the most Mercury-like thing about Mercury. Again and again, the planet sits between categories. It is not just hot, because it also keeps ice. It is not just dead, because it has an exosphere and a magnetic field. It is not simply moon-like, because it is built around a huge metal core. It is not fully protected, but not fully naked. It is not geologically young, but its surface still carries features that may be changing. The more carefully we look, the less Mercury behaves like an endpoint. It behaves like a border between planet and star, between solid rock and escaping atoms, between an ancient interior and a present-day magnetic engine, between a cratered surface and a space environment that never stops touching it. And if the magnetic field shows how Mercury is being acted on now, the ground beneath it shows what happened before. Because the planet's surface is not just covered in craters, it is covered in memory. Memory on Mercury is not soft. It is carved, cracked, flooded, and burned into a surface with almost no air to blur the edges. On Earth, the past is constantly being edited. Rain falls, rivers cut, winds move dust, ice expands inside stone and breaks it apart. Plants grow into cracks. Oceans grind coastlines down. Even when a crater appears, the planet begins removing it almost immediately. Earth is alive with processes that erase. Mercury is different. With no thick atmosphere, no oceans, and no weather in the ordinary sense, The surface can hold a record for an almost impossible length of time. An impact that happened billions of years ago can still sit there, changed but not erased. A lava plain can remain exposed. A fracture can run across the ground like a sentence written in stone. But that does not mean the surface is simple. The easiest thing to notice is the cratering. Mercury is covered with impact scars, from small pits to enormous basins. At first, this makes it resemble the moon, and that resemblance is partly real. Both worlds have been struck again and again by debris left over from the early solar system. Both preserve the violence of an age when the inner planets were still being shaped by impacts. But on Mercury, the impact story has an extra force behind it. The Sun is nearby. Its gravity dominates the region. Objects moving through the inner solar system can arrive at Mercury with tremendous speed, and speed matters more than size when it comes to impact energy. A smaller object moving fast can do extraordinary damage. Mercury's weak gravity cannot easily hold moons, but the planet can still stand in the way of objects falling sunward. It body blocks the solar system. That sounds almost casual, but the record is not casual at all. The surface is filled with bright ray systems, long pale streaks thrown outward from younger craters when impacts excavated fresh material from beneath the darker, more weathered surface. Some rays stretch for hundreds of kilometers. Others reach much farther, tracing lines across the planet like frozen splashes. For a long time, crater rays were not as simple to explain as they looked. In laboratory experiments, scientists tried dropping projectiles into prepared surfaces, but the material often spread in cleaner circular patterns instead of forming long, thin rays. The missing ingredient turned out to be roughness. A surface that is not perfectly smooth can channel ejecta into streaks. The shape of the ground matters. That detail is important because it reminds us that even violent events have texture. A crater ray is not just evidence of an impact. It is evidence of an impact meeting a particular landscape, with particular slopes, ridges, and irregularities. The ray remembers both the object that struck and the ground that received it. Some of Mercury's ray systems are enormous. The crater Hokusai sends bright lines across a vast portion of the planet. Debussy also carries a ray system so large that it becomes one of Mercury's defining visual features. These are not merely decorative marks. They are the visible reach of impacts powerful enough to throw material across distances that would cross entire countries on Earth. Then there is Caloris Basin. Caloris is one of the great scars of the inner solar system. It is roughly 1,550 kilometers wide, large enough that the impact which formed it must have changed Mercury on a planetary scale. The basin is not just a hole. It is a record of an event so violent that it reshaped the crust, triggered or coincided with volcanic flooding, and left rings and plains that still dominate the surface. The name Caloris means heat, and it fits. Not because the basin is still hot in the ordinary sense, but because the event belongs to a period when Mercury was more geologically restless. After the impact, lava flooded parts of the basin floor, smoothing the terrain. What might have begun as a catastrophic wound became a volcanic plain. The planet did not simply take the blow. It responded from within. On the opposite side of Mercury from Caloris lies one of the strangest landscapes on the planet, a region often called weird terrain. The name is informal, but it is honest. The area is jumbled and hilly, unlike the surrounding regions. One leading interpretation is that seismic waves from the Caloris impact traveled through Mercury and focused on the far side, disturbing the crust where they converged. If that is right, then Caloris did not only scar the place it struck, it rang the planet. That image changes the scale of the event. An impact basin is easy to picture as local damage, a giant crater at one location, but on a small dense planet like Mercury, a truly massive impact can send energy through the entire body. The far side may preserve the echo. The surface also remembers melting. Smooth plains cover large regions of Mercury. Some lie inside impact basins. Others stretch across broader lowlands. Their smoothness is not accidental. Lava, once erupted or melted, flows toward lower ground and settles into flatter surfaces before cooling. On Mercury, ancient lava appears to have filled craters, buried older terrain, and created plains that look calmer than the violence that made them possible. A crater with a smooth floor can seem peaceful. It is not. It may be the result of impact energy, internal magma, or both. An asteroid strikes, the crust fractures, heat rises, melt pools, lava fills the basin. Then time hardens everything into a flat floor that looks quiet only because the fire is gone. Some craters show this clearly. Their rims remain rough, but their interiors are smooth, as if the planet poured a new surface into the damage. In some places, mountain peaks or older structures poke through the lava like islands. In others, circular cracks suggest that molten material pushed upward from below, fractured the surface, and then cooled again. This is not a dead rock being passively struck. It is a planet whose interior once answered. Mercury also appears to have had explosive volcanic activity. Certain bright deposits and irregular vents suggest eruptions that blasted material across the surface. Without an atmosphere, the behavior of volcanic ash and gas would not match Earth's skies. But the result could still be dramatic. Material erupted from vents, fell back across the terrain, and left deposits that spacecraft could later recognize by color and texture. A world so close to the sun can still have a volcanic past. That is another reminder that heat from the outside is not the same as heat from the inside. Sunlight bakes the surface. Internal heat reshapes the planet from below. Early Mercury had both. But perhaps the most global sign of internal change is not lava. It is shrinkage. Across Mercury are long curving cliffs called lobat scarps. They formed as the planet's interior cooled and contracted. When a planet shrinks, its outer crust has too much surface area for the smaller interior beneath it. The crust has to adjust. It breaks, thrusts, and wrinkles. One section is pushed up over another, leaving a long cliff-like feature that can run for hundreds of kilometers. Beagle Rupes is one of these scarps, and it helps show how dramatic Mercury's contraction has been. These are not small cracks from local stress. They are signs of a planet changing size. The surface is being squeezed by the slow loss of internal heat. There is something deeply quiet about that kind of geology. No eruption, no impact flash, no sudden plume. Just a world cooling over immense time, pulling tighter around its core, leaving wrinkles in stone. The scarps tell us Mercury's interior evolved. The volcanic plains tell us it once had molten activity near the surface. The impact basins tell us it was struck with staggering force. The rays tell us how fresh material was thrown across rough terrain. But some features still refuse to settle into a clean explanation. One of them is the region around Apollodorus, near the center of a strange network of radial troughs known as Pantheon fossae. At first glance, the pattern looks almost like cracked glass. Long fractures spread outward in many directions from a central region. The obvious guess would be that Apollodorus crater caused it. An impact happens, the ground breaks, and fractures radiate away. Simple enough. Except the crater does not sit exactly at the center. That small misalignment makes the whole picture uncomfortable. If Apollodorus is not truly the source of the fractures, then the pattern may have a different origin. Perhaps the crater came later. Perhaps the fractures formed through volcanic or tectonic forces pushing upward from below. Perhaps the crust was stressed in a way we do not yet fully understand. The honest answer is that the feature remains debated. And that is valuable. Mystery in planetary science is not a failure. It is a boundary marker. It shows where the map has not caught up with the terrain. Pantheon Fossae is a reminder that Mercury is not fully explained by impacts alone, or volcanism alone, or cooling alone. The surface is a layered record, and sometimes the layers overlap in ways that are difficult to separate. A crater may cover an older feature. Lava may bury evidence. A scarp may cut across ancient terrain. A hollow may form later in a place already shaped by something else. The planet is a palimpsest, though not a gentle one. One event rides over another in rock. That is why BepiColombo's future measurements matter so much. Better imaging, better composition data, improved coverage of the southern hemisphere, and simultaneous measurements of the space environment may help connect surface features to deeper processes. If hollows are linked to volatile loss, composition matters. If scarps record contraction, gravity and interior structure matter. If exosphere particles come from specific surface regions, magnetic and particle data matter. Mercury's surface is not just scenery below the spacecraft. It is the archive that all the other mysteries point back to. The sodium tail begins with atoms released from the ground. The magnetic field begins with the interior below the ground. The ice survives because of the geometry of crater walls. The volcanic plains record heat from within. The scarps record cooling. The rays record impacts. The hollows may record ongoing chemical escape. Everything returns to the surface eventually. And that is what makes Mercury so difficult to dismiss. It may look inactive at a glance, but every major feature is evidence of a force that once acted, or may still be acting quietly. The surface is old, but not meaningless, damaged, but not random, silent, but full of instructions for anyone patient enough to read them. The final question is what those instructions are trying to tell us. Because if Mercury has preserved ice, volatile chemistry, magnetic memory, volcanic plains, shrinking cliffs, escaping atoms, and unresolved fractures beside the sun, then the planet is not just a record of itself. It is a warning that rocky planets can be far stranger than they look. Rocky planets can be far stranger than they look, because rock is not always the same as stillness. Mercury proves that in almost every direction. From far away, it seems like the easiest planet to understand: small, hot, cratered, close to the sun. A world with no clouds to hide its face and no oceans to complicate its surface. It appears stripped down, as if nature has already removed every mystery and left only the simplest possible planet behind. But simplicity was the illusion. The closer scientists looked, the more Mercury became a planet of contradictions. It is the closest planet to the sun, yet water ice can survive in its polar shadows. It is small, yet it has an enormous metal core. It rotates slowly, yet it still generates a global magnetic field. It has almost no atmosphere, yet it keeps replenishing a fragile exosphere. It looks ancient and dead, yet parts of its surface may still be changing through the slow escape of volatile material. None of these facts cancels the others. That is the point. Mercury is not one extreme. It is many extremes forced into the same world. The heat is real. On the day side, Sunlight strikes a bare surface without the softening veil of a thick atmosphere. Rock and dust bake under a sky that remains black even at noon. But a few degrees of geometry can create the opposite environment. In deep polar craters, where the sun never reaches the floor, darkness becomes a kind of freezer. Ice can remain protected in a place that, from a simple diagram, should seem impossible. That is Mercury's first lesson. A planet is not defined only by its distance from the sun. It is defined by shape, tilt, shadow, chemistry, gravity, history, and time. The same is true of the exosphere. Mercury does not have air in any familiar sense. There is no wind to feel, no pressure to breathe, no weather to watch. And yet there are atoms moving above the ground, released by sunlight, impacts, and charged particles. The exosphere is not stable, but it is not absent. It is a temporary layer, constantly made and unmade. From that layer, sodium atoms can be pushed away into space, forming a faint tail that most eyes would never see. The tail is almost nothing by the standards of human experience. Too thin to touch, too faint to notice without the right instrument. But scientifically, it is enormous. It tells us that Mercury is not sealed off from the sun. It is connected to it through a steady exchange of matter and energy. A planet is being written into space in atoms. Then there is the magnetic field, one of Mercury's most stubborn clues. It is weak, but it exists. It is offset, compressed, and constantly disturbed by the solar wind. It does not protect Mercury the way Earth's magnetic field helps protect Earth, but it does something just as valuable for science. It reveals that Mercury's interior still matters. A dead core would tell one story. Mercury tells another. Some part of the planet's metal-rich interior appears able to keep a magnetic engine alive. The exact reasons remain under study, but the implication is clear enough. Mercury is not only a surface being damaged from outside, it is also an interior cooling, moving, and leaving signals in the space around it. That gives Mercury an unusual depth. Its story does not sit in one layer. The core affects the magnetic field. The magnetic field affects particles from the sun. Those particles strike the surface. The surface releases atoms. Those atoms become part of the exosphere and the tail. Ice survives because crater walls block sunlight. Scarps form because the interior cools. Hollows may form because volatile substances escape. Everything is connected, and most of those connections are still being refined. This is why Mercury matters beyond itself. It is one of the rocky planets, part of the same broad family as Earth, Venus, and Mars. It formed in the inner solar system, from the same ancient environment that built the worlds nearest the sun. But Mercury followed a strange path. Its giant core, volatile rich surface, weak magnetic field, and unusual geology all challenge the easy version of how inner planets should form and evolve. If we get Mercury wrong, we may be missing part of the story of rocky planets everywhere. That includes planets around other stars. Many exoplanets orbit close to their suns, exposed to radiation, particle streams, tidal forces, and atmospheric loss far beyond anything Earth experiences today. Mercury is not the same as those worlds, but it is close enough and extreme enough to act as a natural laboratory. It shows how a star can sculpt a planet over time, not only through heat, but through light pressure, magnetic interaction, particle impact, and chemical escape. The processes are quiet, but over billions of years, quiet processes become planetary history. This is what makes BepiColombo so important. Messenger gave scientists the first complete modern view of Mercury. but the questions it raised were larger than one spacecraft could fully answer. BepiColombo was built to study Mercury as a connected system, not only as a photographed surface. Its orbiters are meant to examine the planet's surface, interior, magnetic field, exosphere, and particle environment with more complete coverage and sharper context. That matters because Mercury's mysteries are not isolated. To understand the hollows, scientists need chemistry, surface imaging, temperature, and time. To understand the magnetic field, they need interior models and measurements from different regions of space around the planet. To understand the exosphere, they need to know where atoms come from, how sunlight moves them, how the solar wind changes them, and how the planet's magnetic field guides or exposes different areas. One measurement answers a piece. Many measurements together may reveal the machine. And that machine is still running. Not in the way Earth runs, with oceans, weather, plate tectonics, and life. Mercury's activity is colder, harder, more exposed. It is the activity of bare matter under a star. It is rock shrinking as heat leaves the interior. It is surface material being knocked loose by particles. It is atoms glowing faintly in sunlight. It is ice staying hidden in shadow. It is an ancient crust holding the record of impacts so large they may have shaken the whole planet. Mercury does not need to be alive to be changing. It only needs the sun, time, and a surface with nowhere to hide. That may be the final reversal. The planet most people imagine as simple is actually difficult because it has so little cover. Nothing there softens the encounter between rock and space. No blue sky turns radiation into daylight. No ocean absorbs impacts. No thick atmosphere spreads warmth around the globe. The surface meets the solar system almost directly. And because of that, Mercury preserves truths other planets erase. Earth covers its oldest wounds with weather and life. Venus hides its surface beneath crushing clouds. Mars has dust, wind, ice, and ancient climate history layered across it. Mercury, by contrast, holds its scars in a harder light. It is not untouched, but it is exposed enough that its history remains visible in ways that feel almost severe. The first planet is not a leftover footnote beside the Sun. It is a surviving archive, an archive of the early bombardment that shaped the inner solar system, an archive of volcanic heat from a younger world, an archive of contraction as a metal-rich interior cooled, an archive of volatile chemistry that should not have been so easy to preserve, an archive of star-planet interaction written in a tale too faint for ordinary eyes. And maybe that is why Mercury feels so strange once you know it better. It is not dramatic in the way Jupiter is dramatic, with storms larger than Earth. It is not beautiful in the way Saturn is beautiful, with rings bright enough to turn a telescope into a memory. It is not tempting in the way Mars is tempting, with ancient rivers and the question of life. Mercury's power is quieter. It asks us to look at the thing we thought we already understood. The small gray planet, the hot one, the first one from the sun, the world in every school diagram. Then it asks us to look again. Because even there, in the most illuminated part of the planetary family, whole structures can hide until the right instrument sees the right light. Ice can wait in darkness. A magnetic field can whisper from a core we cannot touch. A tail can stretch invisibly through space. A scar can preserve the memory of a world-changing size. Mercury is not the planet where the story of the solar system becomes simple. It is where simplicity burns away. And what remains is a small, dense, battered world still holding questions in the glare of the sun. If this kind of quiet journey through the solar system helps you see familiar worlds differently, Stay with the channel. There are many places in space that look silent from a distance until the science gets close enough to hear what they have been saying.